Today we will continue with the semiconductors. So far we have seen in this topic the distribution function, Phys distribution first, and then the density of states. One was f of e, the other is g of e. So we have calculated the concentration of free electrons in a pure semiconductor such as silicon or germanium. And we have found out that these are, in general, m is equal to some, let me call it c for the time being, and e to minus something. This is the general form. So, in more detail, this is 2 me kBt over 2 pi h bar squared to the power of 3/2 and e to the ef minus eg divided by kBt. So this part, this n is calculated as a result of some integrals. In the previous lectures we calculated them, so this is the result, and it consists of basically two parts. One, the part before the exponential is a certain constant, which is a number, this c is approximately, for some calculations, the practical value is almost 10 to the 25 per cubic centimeter or per cubic meter, for instance. So these are concentrations, so we take the volume as the volume as the particles, number of particles n exist. Therefore, these are not just numbers, they are number per unit volume. So in a certain volume, in some problems it is given as per cubic centimeter basis, in some others per cubic meter basis. The conversion factor is 1 million, remember, 10 to the 6. So in some problems, let's say, for instance, n may be on the order of 10 to the 22 per cubic centimeter. This means 10 to the 28 per cubic meters. This is the conversion factor. So we have to be careful in reading the problems whether it is per cubic centimeter or per cubic meter basis. Similarly for the resistivities, ohm to -1, conductivity also ohm to -1, meter to -1, or ohm meter or ohm centimeter. So you should be careful in solving problems, numerical problems in these topics. So this is the general form. It consists of two parts. A constant part, which turned out to be in this form as a result of the integral, and the more important thing is of course the exponential part. That exponential is the part which is more important in those calculations. And it is a negative term, so it's a dropping exponential. It is related with the temperature inversely, so the temperature is also important. And we have also learned that, unlike the case of metals, whose resistivities increase as a function of temperature, here for the semiconductors this is just the opposite behavior. So the larger the temperature, larger the conductivity as a result, because it means the larger the concentration of free electrons or free holes. And what is the corresponding term for the free holes? Let me write it here. We have P, and for negative, P for positive, remember, and the same behavior, 2 times the same factor, but in this case be careful. Here we have mass of the electron, here we have mass of the hole, and we have seen that even a hole has a mass, is supposed to have a mass, because it cannot react immediately to a force, to a field applied, so it behaves as if it has a mass. Therefore, mH kBt, the thermal energy, divided by 2 pi h bar squared, again to the power of 3/2. Now instead of this exponential, we have another exponential, e to the minus ef only, divided by kBt, for simplicity. These are not very exact expressions, but they are quite good approximations. All right. Then for the intrinsic case, intrinsic means we have also seen in this. Let me just have a short review of the last part of the previous lecture. Intrinsic semiconductor means N is equal to P. So what do we mean by these N's and P's? And we also had an energy picture, and we calculated this. We have seen it as a result of these initially very far away atoms. Later on, they become nearer and nearer to form a solid. If we have only two atoms, these separate energy levels at very large separations. Now they split into two, and this is also split into two, etc. But if we have n atoms, and in general, for a real crystal, of course, we have n atoms, and n is on the order of those very large numbers, very large concentrations, 10 to 22, for instance, per cubic centimeter, etc. Then these are just some bands. So they split into very finely separated, quite near each other, very finely separated energy levels. So a very small, in general, finite amount of energy interval is divided into an almost infinite number of pieces, so that the distance between two successive energy levels is very, very small, delta E. So these are called bands, and if you consider there's a gap here, or there are gaps between the bands, etc. This is the, remember, band theory of solids in general, whether it's a metal or a semiconductor or an insulator, they all have bands, 1s, 2s, 2p, 3s, etc. Remember those electronic configurations of the atoms. And for such an equilibrium separation between the neighboring atoms, remember the lattice parameter, lattice constant A that we saw at the beginning of the term. So for such a separation in the crystal, we have some bands, some empty gaps, and some band again. So this part is magnified, is focused on in a simple picture, energy picture. So this axis is the energy axis, just like this axis. And this is the separation, which is not quite important for this analysis now, because we are considering already the equilibrium separation between neighboring atoms. And here, we have seen that, let's consider that just one part of it. We had these, remember these are the names, energy valence and energy conduction, the two bands. And these, let's show them by solid circles. These are the electrons attached to their host atoms, yet they are not free. They are just bound in those atoms. If you have silicon, silicon atoms, germanium, germanium atoms, etc., or any other material element. So that these are the valence atoms. On the other hand, we have another picture, so we should be able to combine those pictures visually or mentally. So on the one hand, we have these energy pictures. On the other hand, we have the representation of atoms. So for instance, in a certain semiconductor, such as silicon, for example, we have these atoms, neighboring atoms, and those atoms are attached to each other by, remember, covalent bonds. It's a semiconductor. It is the neighboring atoms are, these are all, let's say, silicon or anything like germanium. These are the atoms. And since they are in the fourth group in the periodic table, they have four outermost electrons. So each of those electrons makes a bond with one of the neighboring atoms, silicon atoms. So this one, for instance, let me show just one typical one. Let's finally draw this picture So this is the, for instance, this silicon atom has 1, 2, 3, and 4 outermost electrons. But on the other hand, the others have also the same picture, same behavior, so that, for instance, this one has that, this one has that electron instead of that. So these are the 4 bonds that any silicon atom makes with the neighbors. So it's a diamond structure. In the previous lecture, I had shown the diamond structure. You can have a look if you have forgotten. Alright, so this is the picture. On the one hand, we have these atoms and those bonds, etc. On the other hand, we have the energy picture. If one of them, let's say this electron, for instance, gains sufficient energy to be free, because this is already bound. From a bound system, closed system where the particles are trapped, and we have seen the sort of quantum mechanical picture in the previous lecture, or the one before that, we had seen the infinitely deep potential wells. Of course, in reality, they are not infinitely deep. They are finite wells, but the idea is valid there also. So this electron was trapped, constrained, confined within a certain volume. What is that volume? The volume allocated to a single atom on the average. And that electron, and like the other electrons in that atom, was confined within that small volume on the order of some angstrom cubes, very, very small volume. But if it finds, by some means, optically, thermally, by applying an electric field, etc., if it finds the necessary amount of energy to get rid of that trap, then it can be free. So that this electron is not there anymore, but it is now moving inside the crystal freely, wandering around. But what about the energy picture? Then, for example, this electron was represented by this solid circle. Now it is not in the valence band anymore, it is in the conduction band. And it has moved to the free region. It is now a free electron, so that it is now here and it has this much energy. And that energy difference was called the gap, energy gap or band gap. And we have seen this much so far. Now let's continue from this point on. Now let's have an example first to get more accustomed to the calculations of these topics. Let's find the ratio of the free electrons of, let's say, some material such as germanium to another semiconductor, silicon, at room temperature, for instance. Now this example, let me write it. Estimate the ratio of the free electrons in the conduction band bands of germanium and silicon at room temperature. For this calculation, we need two parameters, which are the energy gaps of these elements, and they are given normally. Eg energy gap of the germanium is roughly 0.7 electron volt, And energy gap for the silicon is roughly again 1.1 electron volt. That's it. So we should be able to find this ratio. For this, let me draw two pictures to grasp the idea. For instance, let's compare, for instance, germanium and silicon. Let's draw two energy pictures, again very roughly. So these are the valence band edges. Since germanium has a shorter energy gap with respect to silicon, let me draw a gap like this. And if this corresponds to 0.7, what is 1.1? It is almost 50% larger. So instead of here, I will draw a level like this. So this is energy conduction for germanium. This is energy conduction for silicon, because of the different energy gaps. And since this is shorter, and let me use the previous expression that I've written at the beginning. So N is some constant. Now we don't need to write the constant in the full form. Anyway, they will cancel. But the rest is important. Exponential part is the important part. The constant, this constant, remember, this C corresponds to 2 times in the parenthesis m kBt over 2 pi h bar squared to the power of 3 half, etc. They will anyway cancel, so we don't write them in the full form. Just C is enough. But the rest is important. Here we have e to the, what was it? EF minus EG divided by kBt. Whether it is silicon or germanium, this is the formula. Number of, not number exactly, the concentration, because concentration is number per unit volume, number in 1 cubic centimeter, for instance. So this is the expression. Alright. Now what is EF? Yeah, EG is given for both, alright, but what is EF? EF, remember, if you talk about the metals, metallic objects, as 0 Kelvin for example, it corresponds to the level of energy where the probability of finding an electron having that much energy corresponds to 1/2 or 50%. However, I had said in the previous lecture that it seems to be meaningless for a semiconductor because anyway there is a gap here. So these are, yeah, let me draw these electrons. There are of course billions and billions of such electrons, and these are the most energetic ones. But if possible, there will be some, let's say, some of them here. These dots correspond to N, little n for germanium, and let me draw a similar picture for the silicon. However, silicon, let me show the number, not the same. So because it has a larger gap, because silicon has a larger band gap with respect to germanium, that number is expected to be less than, that concentration is expected to be less than that in germanium. But how much less? We will see the ratio. Alright. So this is the, remember, this is the energy gap of germanium. That is the energy gap of silicon. This is 0.7 electron volt. That is 1.1 electron volt. Although this difference doesn't seem to be quite an important number. It is a very small, even the difference is 0.4. Even the ratio is not a big deal because the ratio of the difference to one of them is almost 50%, for instance. Yeah, around 50. But this ratio will not be 2 or 3, it will be much more, as we will see, because of the power of the exponential functions. Because positive, as I said before, positive and negative exponential are, both of them are very important mathematically, and they are the predominant terms in such calculations every time. They are much more powerful than the polynomials, the power even the very high powers, of course, trigonometric or any other cases. So E is a very, very powerful function, explanation. Alright, now what is EF? I was talking about EF. Fermi energy corresponds to the probability of 50%, but here, is there any level here where we can find an electron? No, there is no possibility of finding an electron having that much energy. Instead, by convention, they assume that EF Fermi level corresponds to midway, half of it. So this level is expected as the Fermi energy. And here, for this case, this is the midpoint, half of it, halfway. So this corresponds to the Fermi energy. So Fermi energy, EF, is taken to be half of the full gap in such calculations. So we will continue by this assumption. Alright. So we will need N of germanium divided by N of silicon. This is the ratio as the problem tells us. Okay? So this is C e to the EF minus EG. What is EF minus EG? What is EF? EF is half of it. So let me first write in terms of EG and then substitute the data. This is e to the EF. What is EF? EG over 2. EG over 2 minus EG divided by KBT. What is this expression for the silicon? The same thing. The same constant, anyway, they will cancel. E to the EG, but this EG is for germanium. That EG is for silicon. EG, silicon, divided by 2, multiplied minus EG. Of course, this is the same GE, the same germanium, the same silicon. Okay, germanium, germanium, silicon, silicon, divided by KBT. And in this calculation, of course, we cancel these C's, which are almost the same thing for the two types of semiconductors. And what about the rest? Here we have the values of band gaps. So that this ratio turns out to be e to the 1/2 minus 1 is just minus 1/2, remember. So it is negative EG germanium divided by 2 KBT over e to the minus EG silicon divided by 2 KBT. I'll keep this picture on the board. Now, the rest is very simple, of course. How do we continue from now on? So this is the denominator goes up because they are both exponentials. So we have e to the minus germanium 0.7 over 2 minus this is 1.1 over 2 and divided by KBT. So this is just a positive term. The ratio is e to the, now it is positive because 1.1 minus 0.7 is 0.4 divided by 2 and write the KBT here also. KBT. So this is the value we want to find. But the problem says for the temperature at room temperature. And we know very well from previous lectures that KBT, just this part at room temperature corresponds to 1/40 electron volt. So KBT is equal to roughly 1/40 electron volts at room temperature. Whenever we hear room temperature, it corresponds to 300 kelvins, so roughly 27 degrees centigrade, but we don't take the centigrade, remember, it is the 300 kelvins, but KBT this product, if you, of course, if you take 1.38 times 10 to the minus 23 joule per calorie for this and 300 for that, you get something in terms of joule. But joule is too large for such calculations, remember? So we convert it to electron volts by the application of the charge of the electron, 1.6 10 to the minus 19, so that kBT is, please keep it in mind, it is quite practical for several applications, and then it is easily obtained here that that ratio N of germanium divided by N silicon is approximately e to the 0.4 by to 0.2. It is just 0.2 divided by 1 over 40. So 40 goes up over 1 over 40, so that it is just e to the 0.2 times 40, e to the point, this product is just simply e to the 8th, e to the 8th. But what is e to the 8th? Of course, we don't apply to calculators for such simple numbers, simple applications. Let me just write it here, e to the 3. So e to the 3 is just written as, can be written as e to the 8 is e to the 3, e to the 3, e to the 2. And we know again from previous calculation, this corresponds to 20, another 20, and this corresponds to roughly 7.5, 400 times this, so the ratio N germanium by N silicon is approximately 3000. So this ratio, although the energy gaps are very near each other, one is at most 50% higher, larger than the other. But this, in this case, the number of dots here is 3000 times the number of dots here because of the large power of the exponential functions. Now let us see the intrinsic carrier concentration, N sub I, which is an important factor in such calculations. For the intrinsic case, remember, we said that for intrinsic cases, we have said that N is equal to P. So the number of free electrons and number of free holes, and in the previous lectures I talked about the concept of hole, remember, are the same. So if we have, let me draw some circles. For example, in such an energy band diagram, we see that there are here 4 electrons which are bound to their host atoms. But these 2 electrons have already found some energy, that much difference. Now they are in the conduction band. So this is the, remember, conduction bandage, and that's the valence bandage in this energy axis. So here we see that the number of free electrons and number of free holes are the same. So they don't come from anywhere else. We have a certain sample, so that this is a semiconductor, maybe 1 cubic centimeter, for instance. There is no impurity, assume no doping yet, and then whatever number of free electrons there are the same number of free holes. Alright, so this can be found. It's an important factor. If you set these 2 equations equal, those numbers, let's say 2 times this fraction to the power of 3 halves, e to the EF minus EG over kBT, and equal to again the same power, but this time e to the minus EF, etc. They are equal. But if you multiply them, yeah, this is the equality, and from this equality we obtain the, remember in the previous lecture we obtained the Fermi level EF. It corresponds to half of Eg plus some additional term. That additional term was an ln function. And ln of what? Ln of the ratio of the masses. Mass of electron, mass of hole. If they are assumed to be the same, for instance, for simplicity, then ln1. ln1 is 0, so it is just the midway between these energy levels. This is one way. But now we are interested in n times p, the product. If you multiply them, not making them equal but multiplying them, then there are some cancellations. What is that cancellation? E to the plus EF, remember that, n times p, some coefficient, sometimes the same coefficient. Now e to the EF over kBT, if you write them separately, minus EG over kBT, and here we have another minus EF over kBT. If you add them up, so these cancel, we only have the gap as the exponent. So that it's a constant. It is also, the product is constant. And we call it n sub I squared, where Ni is the intrinsic carrier concentration. I represents the intrinsic case. It means özden in Turkish. Intrinsic. Where Ni is intrinsic, because the other possibility is extrinsic. If some foreign atoms are placed, embedded in the system as a doping agent, then it is not intrinsic anymore. Ni is the intrinsic carrier concentration. And that number is generally on the order of 10 to the 10 per cubic centimeter. Then in the previous lecture we had also seen that practically, for practical purpose, because one of the very important topics in solid state physics is the semiconductors, and to deal with, to produce such items in an efficient way, in a with a more capacity, etc. So that intrinsic cases, semiconductors do not have a great concentration for practical purposes. In industry, for instance, semiconductor industry uses some doping elements. In the previous lecture, again, I had talked about those N-type and P-type dopings. Let me cite them by just a few sentences. N-type or P-type dopings. N-type or P-type doping. What was it? Let's remember. Because these are along the periodic table, 3, 4, and 5. These are the groups. And silicon and germanium, remember, correspond to the fourth column group. And if anything, let's say arsenic, phosphorus, arsenic, from the group 5, or boron, aluminium, indium, gallium, etc., one of them from 3, if these are on purpose added to the group 4 elements such as silicon or germanium, then we can have a much greater concentration. Much greater concentration means much greater conductivity, as we see in the following example. Alright, if you choose group 5, this corresponds to N-type doping, because arsenic, phosphorus, etc. have 5, this is group 5, 5 valence electrons in their outermost shell, and group 3 elements have 3. So if you use one of them, this means P-type doping. And we have seen it again before, how they work. When you substitute with very small amounts Those amounts are, remember, 1 ppm, 1 ppb, 1 part per million, 1 part per billion. 1 in 10 to the 9. Remember, this corresponds to, as I said before, a foreigner in India, for example. The Indian population is a bit more than 1 million. 1 million people, 1,400,000,000. Yes, but consider India or maybe China, such a crowded country whose populations are above 1 billion. But if one foreigner, anyone from outside, visits India or China, that ratio is 1 to 1 billion. Even those extremely small concentrations for the doping elements make good work, as we will see. Let me redraw these N-type or P-type energy pictures, just like these energy bands. And then solve an example to see the effect. For the case of N-type, remember the picture we had drawn. For example, N-type case was and that's for P-type. And in each case, of course, we have valence band age, conduction band age. Valence and conduction band age is, of course, in the energy axis. And for the case of the N-type doping, which means we have introduced atoms from group 5, such as phosphorus or arsenic, or any other industrially convenient element from group 5, having 5 electrons, alright? Then they are called donors because they donate an electron, and there's an additional level here. Let's say this is the additional level, very near the conduction band age, and that energy is called E donor. Yeah, there are, of course, these electrons, intrinsic electrons of silicon, for instance, the host atom. But there are some, let me show them by different color. So these are the, let's say these are the, for instance, arsenic. The electrons coming from the arsenic atoms, whose concentration is 1 to 1 billion with respect to the number of silicon atoms. For 1 billion silicon atoms, we have 1 arsenic atom. That's ratio. Alright. Then, normally, at room temperature, for instance, you don't have to heat the sample too much, because if there is no such help, let me call it help from someone else, by itself, if you want to excite these electrons to the conduction band by just heating the sample, you need a very large temperature, maybe more than 1000 kelvins for some kinds of semiconductors. So it is not practical. Until you heat the sample to more than 1000 kelvins, it will melt. So you need some other clever way of obtaining some carriers. Well, those carriers are coming from the arsenic atoms or phosphorus atoms coming from the fifth column. Alright, so these are the, for instance, these are the arsenic. These are silicon. Yeah, silicon atom electrons are still bound to their host atoms. But the others have an energy, it is because of the energy, their energies, they are very near the conduction. So this is on the order of 0.03 electron volt, but this whole gap is approximately 1 electron volt. As is 1.1 electron volt for the silicon. Remember, in the previous problem we used it as 1.1. So this is 1 electron volt, this is 3% of it. Of course, it is much more readily excited to the conduction band, and before these are allowed to move in the conduction band, these are the electrons coming from the arsenic atoms are already wandering around freely in the conduction band. Okay. The other thing is the symmetrical case, where you use an element from group 3, third column, such as boron, aluminum, indium, gallium, one of them. So in this case, the symmetrical situation is this much, but near the valence band. So we have an additional level there. So what is that? What is the help of this in this case? Now we have a certain possible place for these to be excited. So, but there are holes. There are these holes, so they can easily interact with these electrons. So this is also roughly 0.0302 electron volts. Again, this is again to a few percent with respect to the full gap, without the full gap. So these are the cases. What about the new values of the Fermi level? For the intrinsic case, remember, for the intrinsic case, Fermi level was assumed to be midway between the two levels. So this corresponds to Eg over 2. That corresponds to EF, and EF is now, for the intrinsic case, EF was supposed to be half of this full gap. Now, for the case of n-type semiconductors, Fermi level corresponds to here, midway, but between these two levels. So this corresponds to, let me just insert it here, ED, E donor, E conduction. But this dotted line corresponding to midway is the E Fermi, but with an N. Fermi, but for n-type materials. And as you expect for the p-type case, here we have this level is called E valence. That level is called E acceptor, because these are donors. Remember, these are donors, those are acceptors. They donate an electron, these accept an electron, so that they are called donors and acceptors. And again here, just like the previous case in the symmetric situation, we have the dotted line corresponding to the Fermi level for the p-type doping. So this is the new picture. All right. There is also an important terminology for such conductors. N-type, in the N-type case, majority carriers and minority carriers. Similarly, for the p-type case, again, majority and minority. As you expect, in the n-type case, majority ones are electrons, and they are holes. Minorities are holes, because n-type means the predominant type is the negative ones, which is electrons, and the minority ones, whose number is much less than the majority concentration, is the hole. And here we have the opposite case. For the p-type case, majority carriers are holes and minority carriers are electrons. We will use this idea in the following analysis. Now let's have an example, numerical example, for these intrinsic or doped elements. In this example, let's calculate the resistance of a 1 cubic centimeter sample of silicon. First pure and then doped. Find the resistance of a 1 cubic centimeter sample of pure intrinsic silicon. This is, let me say, part A. 1 cubic centimeter sample of pure, which means intrinsic silicon. Part B, find the resistance, assuming that, find its resistance, R, in each case, find resistance R of a, find this resistance R prime, find this resistance R prime, assuming that it is doped with arsenic as 1 ppb, part per billion, and C, find its resistance R double prime, assuming that it is doped with, let's say, boron group 3, again as or with a ratio of again 1 part per billion. So for these calculations we need some constants. One of them is, let's say, Ni, intrinsic concentration. Let me roughly take it as 1.5 times 10 to the 10 per cubic centimeter. This is one parameter. Also, the mobilities are required. Mobility of a free electron, mobility of a hole. This is approximately 1,350. In fact, one can take it as 1,500 for simple calculations. 1,350 centimeters square per volt second for a free electron, and mu h is approximately 450 centimeters square per volt second. And these are the required constants. Part, we have just a pure cubic sample having length 1 centimeter, cross-section area 1 centimeter squared. What do we need for this resistance? We remember from physics 102 how we calculate the resistances. Part A, we have this sample, cubic sample, and this is the cross-sectional area. That part is L is equal to 1 centimeter. Cross-sectional area is equal to 1 centimeter squared. So this is the volume is 1 cubic centimeter over. And we know the formula R is equal to rho times L over A. L is 1, A is 1. What is R? Rho. How do we find the resistivity rho? Of course, rho is inverse of conductivity sigma. Rho and sigma are inverse quantities. Resistivity is inverse of conductivity and vice versa. How can we calculate sigma? Remember that sigma is the sum of two types, contributions from two types, and E mu E for the electrons, P E mu H for the holes. Because we have first the pure sample, the intrinsic sample. So both terms should be taken into account. But also we know that since it is pure, N is equal to P. N and E are constant, we take them out. So that sigma is, we can take N outside, N and B are the same. E also multiplied by mu E plus mu H. What is N? N is Ni. This I, remember, corresponds to the intrinsic case, where N and B are equal. So here we have to write N sub I and N sub I, E and the sum of mobilities. Of course, as I said in previous lectures, mobility of a free hole is 1/3 the mobility of an electron. It is more difficult to move the holes rather than moving the electrons. Alright, now we can make again an approximation to get the result easily. For instance, here let me write the sigma as Ni. What is Ni? 1.45 indeed, but let's take it as 1.5. 1.5 times 10 to the 10 for the intrinsic concentration. What is the charge of the electron? 1.6 10 to the minus 19 coulomb. But what is the sum of them? It is approximately 2000. Less than that, sure, but 1800. But let me take it as 2000, not a big deal. Multiplied by 2000. So we don't have any conversion here because we are only working on centimeter basis, and we don't convert these centimeters to meters, so they will cancel. Alright, what is the result of this multiplication? We have these numbers and a power of 10. 1.5 times 1.6 times a 2, and the rest is power of 10. 10 from the first power, minus 19 from the second, plus 3 from the third. Now, we need one more. Let me add one more parameter. N of silicon is approximately 5 times 10 to the 22 per cubic centimeter. This is the atomic concentration of silicon. We also need that constant, atomic concentration. If you compare atomic concentration with the intrinsic electron concentration, forget about this 5 or 1.5. One is on the order of 10 to the 10, the other is on the order of 10 to the 22. What is the ratio? 10 to the 12, 1 trillion. So only one atom out of 1 trillion atoms gives a free electron as on the average, without any contribution from dopings. Alright, so these are the necessary parameters. So we continue with this calculation. Alright, so what is the next step? Here we have 3 times 4.8, approximately 4.8. Sigma is approximately 4.8 times 10 to what? 13, 10 to the minus 6. 4.8, 10 to the minus 6. But this is our sigma. We have to take the inverse to find rho, and then put that rho in the resistance equation. So rho is equal to 1 over 4.8 10 to the minus 6. So this is approximately 1 over 5, which is 0.2, nearly 0.2. So it is nearly 0.2 10 to the plus 6, so approximately 2 times 10 to the 5 is rho. So put it just here, put this rho in this previous equation for the resistance. Then resistance R for this pure case, intrinsic case, very approximately rho times 1 over 1. We don't need the conversion here from centimeter to meter. So this is approximately 200 kilo ohms. 2 times 10 to the 2, 10 to the 3. So 2 times 10 to the 5 means 200 times 10 to the 3. So it is approximately 200 kilo ohms. Such a resistance for the case of pure sample, intrinsic case. Now we will see the effect of doping, even with a very small ratio, 1 part per billion. A foreigner in India, remember. So part B. Now, again, R prime now. R prime is equal to rho times L over A. Alright. But what is rho now? Rho is equal to 1 over sigma. Sure. But what is sigma? Now, sigma is equal to, the sum of these two terms at first sight. But one of them will disappear soon. So it is N E mu E plus P E mu H. What is N? N is not Ni anymore. N is not Ni now, because this is not a pure sample. What is the new value of N? It is the new value of N is found by N is equal to number of donor atoms, and that number of donor atoms is N silicon divided by 10 to the 9. Please try to see the difference between silicon atomic concentration and the intrinsic electrons. Intrinsic electronic configuration, the electronic concentration, remember, is 10 to the 10 billion, maybe 10 billion, 10 to the 10. A small, relatively small number, because the other is 10 to the 22, 1 trillion times greater. What is that greater number? It is the atomic, in one cubic centimeter, in such a small volume, there are 10 to the 22 silicon atoms, but only 10 to the 10 free electrons coming from those silicon atoms before any doping. After doping, there are some carriers, additional carriers, because of the N-type doping. How many are they? That number is found by dividing by 1 billion, but this is the number to be divided. What was that number? Atomic concentration was, remember, 5 times 10 to the 22 divided by 10 to the 9. This corresponds to 5 times 10 to the 13. It is 1,000 times greater than the previously free electrons of silicon. That's why there's a large effect by doping. Now we will find the calculations. Alright, then N turns out to be approximately 5 times 10 to the 13. Of course, the units are per cubic centimeter. We don't convert to cubic meter in this problem, in any part. Alright, listen. Then what is P? Yeah, this much, and it's alright. But what is this second part? We don't have N equals P anymore. Be careful, this is not an intrinsic case. In part B, we have doping. So we have to find P now. What is P? Since we know that N is not equal to P anymore, we have to find the new value. The new value of P is found by N times P. Remember, we derived this equation in the previous part. N P is Ni squared. Whether it is a pure case or an N-type case doping or a P-type doping, this formula is valid. What is the new value of n? 5 times. So this is the new value now. This is our n. What is p? We know n squared anyway. So n is 5 times 10 to the 13 multiplied by the unknown p. What is the right hand side? It is 1.5 10 to the 10 squared. It is 1.5 10 to the 10. Don't forget to take the square. So p is approximately 1.5 squared times 10 to the 20 after the squaring divided by 5 and 10 to the 13. So this is approximately 1/2. 2.2 over 5 is approximately 0.5 for this part times 10 to what? Only 7. So it is 5 times 10 to the 6 per cubic centimeter. Now if you compare n and p, which one is larger? Of course n, because this is an n-type loading. How much larger? By an astronomical ratio. 10 to the 13 divided by 10 to the 6. The ratio is 10 to the 7. 10 million. So if something is smaller than the other by a ratio of 1 over 10 million, we neglect in physics the smaller one. Please keep it in mind always. Alright, now, and let me rewrite them to compare. N is equal to approximately 5 times 10 to the 10 to the 13 per cubic centimeter. The other is P is equal to only 5 times 10 to the 6. So here we understand that P is much less than N. So P is negligible. We don't add the second part to the conductivity. In physics, remember, let me write it as a motto. In physics, if a quantity, please don't forget these important points. These are general suggestions. In physics, if a quantity such as n is much larger than the other, such as P in this case, so we have that n is much greater than P, then the smaller is neglected. Even by a ratio of 1 to 100, 1 to 1000, you can neglect. What is the ratio here? 10 to the 7. N over P is approximately 10 to the 13 by 10 to the 6. So the ratio is 10 to the 7. 10 million. If N is 10 million times P, then of course we simply drop the smaller one and don't add it in the calculation. Therefore, what is the new sigma? It is approximately n mu e, that's all, plus nothing coming from the positive part. Alright, and n mu is easily calculated. What is the new value of n? It is now 5 times 10 to the 13. 5 times 10 to the 13 multiplied by the charge 1.6 10 to the minus 19, and only the mobility of the electron, which is roughly 1,500, 350, but let me take it as this much and write the result here. Alright, so sigma is approximately, if you multiply these, this is 8. 8 times 15, 120. 120 for the first part times 10 to what? 13 from the first. minus 19 from the second, and 2 from the last, so that it is approximately 1.2, 2 more, minus 10 to the minus 2. This is sigma. For rho, we have to take the inverse. Rho is equal to approximately 1 over 1.2, 10 to the minus 2. Then, the resistance R prime is rho L over A. What is rho? 1 over 1.2, 10 to the 2, minus 2, times 1 over 1. So this is approximately 100, a bit less than that, maybe, let's say, 80. Okay? Then R prime is approximately 80 ohms. Alright? Such a large effect, such a large drop in the resistance. What was R? Remember, in the first part, R in the intrinsic case turned out to be 200,000 ohms, 200 kilo ohms. From 200,000, it dropped to only 80 as a result of even such a small doping, 1 part per billion. Alright, now what is the difference between part B and C? There is a third part in this problem where you make a p-type doping. In the case of p-type doping, the only change is in the mobility. Part C. The other parts are made by the same idea. If it's a p-type doping, if some boron atoms are used for p-type doping instead of an n-type, then what happens? Sigma will be, in this case, Ne mu E plus Pe mu H. This is the equation, but this time, first part is neglected totally, because now P is much greater than N. Alright? P is much greater than N. Now in this case, what is P, what is N? P is equal to, again, number of silicon atoms divided by 10 to the 9. So this is 5 times 10 to the 13, again, 22 over 9, 10 to the 13 per cubic centimeter. But N, what is N? N times P is Ni squared, so that N turns out to be approximately 1.5 10 to the 10 squared by this ratio, 13, so that N is on the order of 10 to the 6. Again, the ratio this time, pure N is approximately 10 to the 7, just the symmetrically opposite case. So N is neglected with respect to P, but we don't get the same resistance because of the difference in the mobilities. Otherwise, we would exactly get the same value for the resistance. But now, instead of mu E, we will use mu H. Now, since mu H is not the same as mu E, we will have a different result. We will have sigma is equal to P times approximately Pe mu H. P is 5 times 13 multiplied by E, which is 1.6 10 to the minus 19. But the mobility for it, let's say 450, let me take it as 500. So this is approximately 500. So that sigma will be 8 times 5, 40, times 10 to the 13 minus 19 plus 2. So let me go back here. Instead of this number, we will have 1/3 of it. Sigma will be approximately 0.4 10 to the minus 2. So that rho will be 1 over 0.4 10 to the minus 2. And final resistance R double prime will be since rho is greater, this will be almost 3 times, roughly 240 ohms. Alright, 240 ohms. Again, it is a very large drop from the intrinsic value of 200,000 ohms down to maybe 80 ohms only for the case of n-type doping, maybe at most 240 ohms roughly for the p-type doping. So this is one of the many advantages of these semiconductors. It is not only, semiconductors not only fall in the midway part for the conductivity scale between the very good conductors and very good insulators. It is somewhere corresponding to the middle part. But not only that, there is also one more advantage. You can play with the conductivity by just changing the concentrations of the doping elements. Because if you change this from, let's say, not from 1 part per billion to 1 part per million, for instance, if you just make it 10 times larger, 10 times smaller, by playing with the concentration of the doping elements from group 5 or group 3, you can play with the conductivity and in turn play with the resistivity and therefore the resistance of the whole sample of this macroscopic size. So this single object having a volume of 1 cubic centimeter for the silicon, in the intrinsic case it has a very large resistance of 200 kilo ohms, but by just introducing some very, very small amounts of extrinsic elements, such as group 5 or group 3, as a result of this very little introduction, the resistance drops abruptly to a much, much smaller value. So you can play with the resistivities, conductivities by just adjusting the level of doping. Now in this part, let's consider the optical properties, because there is some light maybe coming in, maybe in the form of visible light, maybe in the form of some infrared light or ultraviolet electromagnetic radiation, and see if it works for these semiconductors, if it gives any good outcome. Let's see. Now let's consider the optical properties, and let me simply ask a simple question. We may have a sample, for instance, very thin foil, so it's aluminum foil, for example, which is very, very thin, that we wrap for some sandwiches, for example, some foils, golden foil, or any kind of a very thin plate which can be used for wrapping some packages. If you send some light from one side, then that light cannot pass through generally. However, if you consider a piece of a glass, for instance, having a considerable thickness, maybe a few centimeters, maybe more than that, however, the light sent from one side passes through the other side, although the intensity gets a bit less, but it just does pass. So what is the reason? Although in the first case we have a very small thickness, maybe on the order of some micrometers, maybe much less than 1 millimeter, but the light is just reflected back, maybe, so it doesn't pass through. So on the other side you cannot see the light coming in, the incident light. However, if you have a piece of maybe some glass sample or some mica, so that type of thing, you can see the light coming from the other side of the specimen. So what is the reason? For example, let's compare two materials having the same element, carbon type of thing, for instance, or some, let's say, diamond and silicon having the same atomic structure. The silicon, if you use some silicon sample, the light does not pass through. But if you use some diamond, it can. This can be considered as the following, in the following way maybe. Because we have drawn these energy pictures, and here we have these valence band electrons, and for example, if some light is coming in, some incident light, with a certain frequency, of course, as I said in the previous lectures, this may have some frequency nu. So it has some energy. That energy is, remember, h nu, or we can write it as hc over lambda, h times c over lambda. Nu is the frequency in terms of hertz, and lambda is the wavelength in terms of meters in general. C is the speed of light, h is Planck's constant. So this is the energy of the incident particles, photons. Now, on the other hand, we have the band gap. This is the band gap of Eg in terms of some, on the order of some electron volts, maybe 1, 2, 3 electron volts. 1.1 for silicon, 5.5 for diamond. All right, this is the picture. If there's a condition, if this E is on the order of an bit larger than the band gap, then these photons are able to excite some electrons from the valence band, and therefore this is now leaving behind an empty place, a free hole, and it is excited to the valence, to the conduction band as a free, this is a free hole, that is a free electron. And the photon disappears. So the photon disappears, but now we have an electron hole pair. Or until then, if there are n electrons in the conduction band and p holes in the valence band, then this becomes n plus 1, that becomes p plus 1, because there is an additional electron hole pair now, and the photon is just disappearing. On the other hand, we have the opposite picture. If, let's say, this is the creation of an electron hole pair. Now the annihilation part is a free electron drops back. Drops means it doesn't drop as a result of the gravitational attraction. It drops in the energy sense. Its energy now drops from conduction value to valence band value. So it gives off this much energy backward, so that in the opposite case we have initially n and p. Now this becomes n minus 1, that becomes p minus 1, but a photon is created, and a photon of energy E, let me say Eg, this much energy, having this much, a photon of energy Eg is created. So these two types of devices are, in the first case we create pairs. So this is like a solar cell, for instance. Some light energy, electromagnetic energy is coming in, it is incident. As a result, we create some carriers, and those carriers, if they are oriented through an external circuit, they create a current, solar cell. So as a result of this solar energy, or the electromagnetic energy of these photons, we create some current, electrical current in the circuit. Or oppositely, you initially have those carriers, but if they annihilate each other, what is the annihilation? Now, this is the first process. The opposite process is, now we have, let's say, there's only one free electron, but these are the valence electrons. And here is the free hole. If this one is dropping in energy and uniting with this position, free hole, then N becomes 1 less, P becomes 1 less, and as a result, some photon is created. So this photon is created with an energy of this band gap of Eg, so many electron volts. So depending on the type of material, we have different, remember, bandwidths, Eg, values are changing. And this is the operation mechanism of LEDs, light emitting diode. Whenever you use an electronic device, you may see in front, maybe just on the surface, you may see some green light or red light, small pieces of light. Those lights are called LEDs, light emitting diode. And in short, they are called LEDs. Depending on the gap width, that bandwidth, a different color can be created. If you create another material having a certain bandwidth, then the gap for this band gap, then the corresponding color can be obtained as the output of this LED. All right. So why do we have some view on the other side of the glass, but quite a thick sample? However, we don't see the incident light for the case of the very thin foil of some other opaque object. Let's briefly talk about it in terms other than physical terms, maybe. Assume that we have a conveyor. We are working in a factory. All right. So let's say we are working here. There is some conveyor belt. So this is the conveyor belt. So it is continuously passing in front of us. We are the workers. Let's say we are some working people here. But there is some rule, for example. Each worker, because all the workers are older than 20 years, for instance. All of us are older than 20 years. So we are not children. However, there is a rule stated by the factory which states that if you find something on the conveyor belt which you can use personally, you can take it. Right? That's the rule, for example. So we are some people here, all of us are adult people, but you can take them for your personal usage. You cannot take them and sell somewhere else. So this is the main idea. If you can personally use this product passing in front of you, you can take it. Otherwise, you just leave it. It is the rule. And assume that the products passing in front of us are some shoes, but shoes for children. For example, for 8 years, 10-year-old children. So none of us can make use of it personally. So we just look at those products and they are just passing by us. So we are the crystal, and here are the photons that are passing because we cannot take them. They are useless for us. But if instead of us there are some children here, they can use those shoes because they are applicable, they are convenient. Those products are convenient for those groups of children because anyone can take a pair of shoes and makes use of it. So this is the main difference. If you are the people who cannot make use of the product, then you just see them pass through. But if it is convenient for you, if the product passing in front of you is convenient for you, you can take it. If you can take it, there is no output here. There will be nothing. Because there are, let's say, n people here, we have, let's say, 40 people working. All of us are adult people. And 40 pairs of shoes, or more than 40 shoes, are passing, but they are shoes for children, so that they are just passing without any loss in number, because none of us can take any of them. However, if there are n children, let's say 40 children, boys or girls, 40 children, and there are, let's say, 40 pairs of shoes, each one can take one of them, and there is no output, just like in the case of the silicon and diamond. Let's now compare the numbers. Example. Explain why silicon is opaque but diamond is transparent for visible light. Now we need two parameters, of course, as you expect. They are both the band gaps of these two types of materials. E.g., that we have seen a minute ago for silicon, 1.1 electron volt, and this is for the silicon, and E.g. for diamond, this is around 5.5 electron volts. So this is the picture for one, this is the picture for the other. Now 1.1, this is the case for silicon, that is the case for diamond. If this much corresponds to valence band and conduction band age, so this difference is just 1.1 electron volt, 5 times larger gap, so this is 1, 2, 3, 4, 5 times larger. Such a gap exists for the case of diamond, and that is around 5.5 electron volts for the diamond. Now compare the light coming in. For silicon, in order to absorb the light, the minimum frequency can be found. For silicon, the minimum frequency, let's use now the frequencies, not the wavelengths for the visible light. Of course, the same analysis can be conducted through the wavelengths as well. For silicon, the minimum frequency of light is what is that? E min, which is H nu min. That has to be the gap, 1.1 electron volt. You can consider the conversion from electron volts to joule, etc. for the case of lambda, for instance, or E is equal to, remember, also Hc over lambda. But if nu is minimum, lambda should be maximum. This is also applicable. Now in this case, this is something aside. Now use this first equation. Nu min is just 1.1 electron volt. But in order to use the value of H for the as the well-known value of 6.6 10 to the minus 34 in terms of joule second, so that we have to convert it to, let me write it here, So new min is just 1.1, but converted to joule, so we have to multiply by the charge of the electron. 1.6 10 to the minus 19, this is joule, divided by H. 6.6 10 to the minus 34 joule second. So that joules cancel, we will have 1 over second, which is hertz, as the unit of frequency. So what is this expression? We can use rough calculations, of course. Now, what do we have? Maybe 1 over 4, 1 to 4. 1.4 over 4. So new min is approximately 0. Let's say 3. Okay? So this is 4 times that, 1.2. So this is approximately 0.3. What is the rest? Power of 10, it is 10 to the 15. Okay, 34 minus 10 to the 14. So it is 3 times 10 to the 14 hertz. Alright? Now let's leave it there and pass to the case of diamond. For silicon. For diamond, okay, for diamond, we have the same idea, same formula. Nu H, nu min is equal to, this time we don't have 1.5, we have 5.5. 5 times larger. So we have 5.5 electron volts. Again, nu min can be calculated by this conversion. Nu min is 5.5, 1.6 and the power of minus 19 divided by, again the same H, minus 34. So what is the resulting value? Now these can be simplified by 5 over 6. Okay, so this is again 4, 1 to 4. So 5 over 4. 5 over 4 is approximately 1.25. And the rest is, so this much is that. 10 to the minus is plus 15. So we have nu min is 12. Now in order to compare them, let's make the powers of 10 the same. So we have 12 times 10 to the 14. We should have 12 times 5, 10 to the 14 hertz. Alright. Now what is the other piece of information we need? What are the limits of the frequency for the visible light? For the wavelength, we know that it's approximately between 300 nanometers and 700 nanometers, very roughly. Between 300 and 700 nanometers for the wavelength. But here we obtain some results for the frequency. For the frequency, we have 4 to 8, 10 to the 14 hertz for the visible light. Either you convert them to wavelengths by this expression, or compare these data with the interval of the frequency values. So the visible light, for the visible light, nu has to be less than or greater than 4 times 10 to the 14 hertz and 8 times 10 to the 14 hertz. What are these results? 3 times that. So it is something less than the lower value, lower limit. Of course, this cannot be used. And here we guess, this is, for instance, here, 12.5. It is above the value, necessary value, so that the frequency of 3 times 10 to the 14. 3 times 10 to the 14 was the lower value. The minimum value was 3 times that. But this is already 3 times 10 to the 14 corresponds to somewhere here along this. Let me draw this as a scale, one-dimensional frequency axis. So this is the frequency axis. The critical values are 4 times, this is in terms of 10 to the 14 hertz. So the values are 4 to 8. So this part is corresponding to the visible part. But for silicon, minimum value should be this much to be absorbed. It is somewhere here. So these values are more than the enough satisfactory values. Of course, they are absorbed. So visible light is absorbed by, so we understand that visible light nu between 4 10 to the 18, 10 to the 14, nu less than 8 10 to the 14 hertz. Visible light is absorbed by silicon. This is just like the shoes for children, and the people are already some children. So those objects are taken up by these waiting people. So there's no output, because this is convenient. The product is convenient for the waiters. Therefore, they are used, they are absorbed by silicon. However, for the case of diamond, minimum value, if diamond has to accept something, it should at least be of the frequency of 12.5. But the visible part is here. One is, let's say, 3 for the silicon. Let me show them differently. So silicon here, but diamond there. For the diamond, the minimum frequency to be used, to be absorbed, was something 12 times 10 to the. However, the visible part of the spectrum is not enough for the frequency. So that diamond is like us, the adult people, who don't take any of the pair for children. So that for diamond, those pairs of shoes are passing in front of us. We don't take any. But for the case of silicon, the people for silicon are already some children, so that they are taking, each one is taking one shoe from the conveyor belt, so that none of the shoes is passing to the end part. Okay, so this is a kind of parallelism. In some cases, we have some combinations of materials, alloys, for instance. Instead of 2 materials, 2 elements, A, B, sometimes one may have A, B, C. So, again, using the periodic table, for instance, gallium arsenide. Gallium arsenide, for example, this is the periodic table. These are the columns 3, 4, and 5. And gallium is something in the 3rd column. Gallium, arsenide is from the 5th column. And also remember that in the, as we talked about in the p-type doping, gallium and indium are from the 3rd column, and arsenic from 5th column. So gallium arsenide and indium arsenide, for instance, are 2 possible combinations. but sometimes it is a combination of gallium and indium together with the arsenic part. And now let's see the percentage necessary to create a certain band gap. Now in the next example, let's focus on this point where we can have more than two types for the first part. Some percentage of gallium and some percentage of indium together with the arsenic atoms. Gallium arsenide and indium arsenide have band gaps of 1.43 electron volts and 0.36 electron volts respectively. So the numbers are not too important, but the idea is rather significant for the physical point of view. Gallium arsenide or indium arsenide, so which means if all the gallium atoms are replaced with indium atoms, we have a different band gap. Alright, what should be the percentage of gallium atoms should be replaced by rather? What percentage of gallium atoms should be replaced by indium atoms so that the light of or the electromagnetic radiation of 1 micrometer light of wavelength, the light of electromagnetic radiation is better, so that the electromagnetic radiation of wavelength 1 micrometer is absorbed. So let's compare the two cases. First of all, let's try to understand. There's an assumption, of course. Assume that the energy gap changes linearly between the two cases. So if you compare these gallium arsenide and indium arsenide, for the case of gallium arsenide and for the other one, and the gap is, let's say, 1.53, 1.43. Let's say this gap is around 1.43 electron volts. And for the other case, it is almost 1/3, less than 1/3. Less than 1/3. So this is the case of 0.36 electron volts. Okay? And also the final assumption says that it's a rather linear relationship. So which means we have the following. Now this is not the energy picture. This is the XY plane, for instance. In the first case, let's say we have 1.43 which is corresponding to the full gallium and arsenide. Arsenide, as far as arsenide is concerned, there is no change. Now for the other part, indium, we have roughly this. Alright, 0.36. So, and assume we have a linear function, roughly. So we have sort of such a function between totally gallium and totally indium cases. Of course, the other part is arsenic, sure. But we are interested in how much or with what percentage should we have gallium, with what percentage should we have indium. This is 100% gallium, 100% gallium, 0 indium. This is 100% indium, 0 gallium. And first of all, we should find the energy corresponding to this number. 1 micrometer, yes. Wavelength 1 micrometer. If wavelength is 1 micrometer, what is the energy corresponding to that? And then we will find that energy along this scale, and by just interpolation, we can find the percentage of gallium to indium. The energy corresponding to this wavelength, the energy E corresponding to the wavelength of 1 micrometer, the wavelength of lambda equals 1 micrometer is what? E is equal to hc over lambda. hc, let's use the known data. H is 6.6 10 to the minus 34 multiplied by the speed of light 3 times 10 to the 8 divided by lambda, 1 micrometer, 1 times 10 to the minus 6, 1 times 10 to the minus 6. As a result of this calculation, the result will be in terms of joules. After that conversion, we will have in terms of electron volt values, and then we will see where it corresponds to. Alright, this is relatively simple because we have 3 times, roughly 20, 3 times this 20 times 10 to the minus 34 plus 8 plus the 6 coming from down. So it will be 2 times, one more 0 here, on 10 to the minus 20, 10 to the minus 19, 10 to the minus 19 joule. Now if you divide it by the conversion factor, now converting it to electron volts, we have 2 times 10 to the minus 19 divided by 1.6 10 to the minus 19. So we will have approximately 5 over 125, approximately 1.25, and they cancel, electron volts. Once we have obtained this necessary value for the energy, go back to the previous picture, 125. Where does it correspond to? 143. So 1.2, this corresponds to somewhere here. 1.25. And by just some interpolation or extrapolation here, we can find the percentage there. But for this purpose, we need a function. That function is, it is just like a, for instance, y is equal to mx plus n type of function. Linear. It has an intercept, it is a negative slope. What is the negative slope here? It is this ratio, this difference by that difference. Let me call this difference by 100 units, because 100% gallium or 100% indium. So we can take the base as 100 units, but that difference corresponds to 1.43 minus 0.36 over 100. Now let's continue here. Then it is almost 1.07 over 100, and it is approximately 1.07 times 10 to the minus 2 for the slope. So y is equal to negative, remember this is a negative slope, sliding down, minus, this is a negative slope, minus 1.07 times 10 to the minus 2 times x plus the intercept of 0.36. 0.36. And this y, if y is equal to 1.25, which is the required value, 1.25, then what is x? This is the problem. 1.25 on the left hand side, negative, this is approximately 1. Let's, it's not a big deal. So minus approximately 10 to the minus 2 x plus 0.36, so that x will be 1.25 minus 0.36 divided by 10 to the minus 2. No, sorry, this is not the intercept. Intercept is point, sorry. We made a mistake for intercept. It is not 0.30, it is the starting value, 1.43, sorry. So this is 1 point, So the intercept here and corresponds to this value, and the slope is the slope of this line, alright. M is a negative number, but and the intercept is 1.43. 1.43, alright. So 125 is the required value for y parameter. This is the x part plus 1.43. So this is 1.43 divided by this approximately. X is, and this is negative also. Now it is positive, sure, because 2 minus signs will cancel. 0.18, 0.18 by 10 to the minus 2, so it's 18. So that x corresponds to 18%. So 18% of gallium should be replaced by indium. So gallium corresponds to 100 minus 18, so this is 82%, and indium should correspond to 18%. This is the expected distribution between the two types of atoms together with the arsenic. Now in this section, let's consider the junctions, also an important part of p-n junctions. Because so far we have seen p-type and n-type separately as two distinct types of semiconductors. Now let's see what happens when they join. Now, before we consider the p-n junction, let's consider a metallic junction. For example, we have a teaspoon of metal A and a key of metal B. I don't know exactly what they are. Maybe the teaspoon can be silver or some other element. But the key is also possibly a combination of some metals. However, they are of different elements. And if you just touch them, join these two different metals, you construct a contact. It is called in general a contact Now before p-n junction, let's consider metallic junction. If we join two different metals, now what happens? Let's say we have one metal and another metal separately. So this is metal A, that is metal B. But they have different work functions. Since the type is different, there's a difference in the work. What's the work function? It is the minimum amount of energy necessary to detach an electron from the system, so that, let's say, this corresponds to some amount this much, and that corresponds to this much. So this difference, let me call it phi sub A, and that difference is, let's say, phi sub B. And these are not touching each other yet at different positions in space, and there's no junction. But if you bring them together, what happens? Let's say, when you bring them together, we have the first, let's join them. Phi sub A, phi sub B, and just after these are the field states. This is just after joining. But this second case is not stable because it is impossible to remain as it is. What will happen immediately is the following. Let me just have another simple analogy. For example, you want to have some interaction with some ATM, automatic transaction machine. Let's say there are some ATM. Some ATM, another ATM, side by side. Okay? And normally, let's say this is the top view, and there are people waiting in line. For instance, there are some, and the system is closed. So these are just like tunnels, for instance. So there are some people, and this is closed, and this is a person in line, and you arrive here. You have two choices: either you enter the first line or the second line, but you don't know how many people there are in the line waiting for the operation. Okay. If you have no idea about the number of people waiting in line A or line B, it is up to you. You either decide to enter the first one or the second one. All right, but assume that at a certain moment, this let's say screen is taken away, and people realize that there are, for example, you are here, you want to make a decision which line to enter, but people here, especially these people, understand that there are empty places in the other line, so that maybe this person just passes there, this person passes there. You also choose this way instead, because there are several possibilities in one with respect to the other. So this is an example from outside physics. Okay. Now we go back to the physics. What happens here when you join these two different metals, metal A and metal B, having different work functions, phi A and phi B? What happens immediately after? These lines, because these are corresponding to the Fermi levels. So Fermi levels, Fermi levels align. Yeah, these are, so this is the case. But then the system is like that. Because the shorter one is here and longer one is there. And these are the electrons in the valence bands. So these people correspond to those electrons. So just like these people who realize that there are empty places, available places in the other line and pass immediately to the other line where there are more possibilities, these electrons now, because of the difference in the work functions, immediately move to the empty places in the other type of metal. So there is now a flow of electrons from because of the electrons in metal A. The electrons are especially this part, this above the line. The electrons in A pass or have a tendency to pass to the available places in metal B, to the available places in metal B. So at the end they try to be equalized. So just like these, now instead of 6 and 2 people here, we have 4 to 4. Almost equal division occurs also here. So these electrons having energy more than the average value now have a tendency, they try to move to the other part. So what happens then? Then there is a contact potential. Then there occurs a contact potential phi. What is that phi? It is the difference of phi B and phi A. There occurs a contact, because now we have a contact, they touch each other. A contact potential phi, and that phi is equal to the difference of these two work functions. Of course, if we join two similar metals, a silver teaspoon with another silver teaspoon, there will be no contact potential because each one would have the same work function. Since they are dissimilar metals, metal A and metal B, and the work function is peculiar to the type of element, therefore there is a difference, and because of that difference, the more energetic ones in one try to go to less energetic places, available positions in the other one. But as a result of this, there is a contact potential occurring on the order of some, let's say, millivolts, very small. However, there is a certain contact potential. It is generally represented by capital phi. Now we can consider the p-n junction for the semiconductors. Let's draw a p-type material first and an n-type material. We have a p and an n. What are they? Let me show the, or rather draw them side by side. So this is the p-type and that's the n-type. Let me draw the energy pictures. Okay, so this is energy balance, energy conduction, similarly here. But as you see, in the n-type case, there is an additional level here, which is, let me draw the additional level as E sub D, D donor. No, so n-type here, sorry. N-type, we have this additional level here called the ED, E donor, and for the p-type we have an additional level here, which is a few percent of the full gap. So this is the case level for E acceptor. On the other hand, we have seen that the new Fermi levels for the doped cases correspond to somewhere in the middle. So for example, this is the level for the case of E, F for the case of P, and here we have in the case of E, F, N. But just like these two levels in the case of two metals, two dissimilar metals equalized as a result of this junction, they join each other. Here also the Fermi levels EFP and EFN get aligned as a result of this junction, as a result of joining the P and N-type materials. But this is, let me immediately say that in reality, in production processes, this is not obtained by just taking a piece of N-type material and a P-type material and just touching each other, etc. We form a PN junction. This is not the way they follow. Instead, they take a single intrinsic sample at the beginning, for instance, from one end. Let's say this is the P-type end, this is the N-type end. From the P-type end, they inject. Remember, we have seen in the diffusion, in the previous lecture, we had seen the diffusion process. By injecting those P-type carriers, holes from one end, and from the other end, by injecting the N-type carriers, free electrons, they create the PN junction in the single element. So when they meet each other near the middle part, a PN junction occurs. So this is not just, as I said, taking two different pieces and joining them together. Instead, one single item is doped differently from the left end or the right end, so the PN junction occurs near the middle part. Next, so how do these levels get aligned? Alright, now take this one and create a certain slope here, contact potential. In this case, bring this dotted line and join it to the other dotted line. So we have the alignment of the Fermi levels. So we have the Fermi levels aligned. Then what happened to the other lines? So for the P-type, remember P and N, this is the order in this case. Don't play with the order. So we have this P and N. But here there is a slope. So this is the contact potential, and that difference, this difference corresponds to the contact potential phi. Alright, I don't make it too crowded with writing some other parameters, but this is the main idea. And what happens, this is the energy picture. So Fermi levels align, but of course this is the P-type, that is the N-type, and here These are the valence and conduction band edges for the one and for the other. Okay? And these dotted lines are the Fermi levels. Immediately after we join these two pieces of semiconductors. Okay? What happens? This is the contact potential. So there is a certain probability of, again, let me immediately emphasize that the things are probabilistic. So remember the Fermi-Dirac distribution every time you face with such processes, because it depends on the probability, first of all. And as the energy difference gets larger and larger, it becomes less and less probable to climb that hill. Okay, so the smaller the difference, okay, the smaller the difference, the more likely it is, more probabilistic it is to climb the hill. Which hill? This is the hill. Energy hill, sort of. Okay. Now there is a certain flow, but there are two types of carriers: free holes and free electrons. Now let's consider the contact through the other point of view. Let's now consider this, that is called the PN junction. So this is the PN junction. Now what happens in this picture? Let me draw it maybe here. So let's draw the picture, this time considering the carriers. Now what do we have here? Remember always that this is the p-type, that's the n-type. In the p-type, and there are also, let's say, these particles. And what are the meanings of these symbols? This is the positively charged ions. Positive ions. These are free holes for the red one, for the black ones. And red ones are negative ions. And these are free electrons. First of all, there are ions everywhere. Ion is an atom. If it is a positive ion, it means it's an atom who has already lost an electron. If it's a negative ion, it's an atom having already gained an electron. Alright. So in the p-type part, there are, of course, since it is p-type, there are free holes more than free electrons. So first of all, there are free holes here. There are free holes like this. And free electrons are here. Of course, there are other types as well. If you red ones, and here if you black ones. Minority, majority. Remember, these are the majority carriers are in the p-type case, p-type part. Majority carriers are free holes. In the n-type part, Majority carriers are free electrons, but there are also minority carriers which are opposite sign. So here we have some red dots corresponding to free electrons, here some black dots corresponding to free holes. What about the ions? Ions are here, in this case, we have what? Positive free holes. Free holes means some of them have lost, so there are negative ions here. And for the other part, we have just the opposite case of positive ions, because there are some much more free electrons. So there are these here. Okay, so this is the basic picture. Please try to understand what happens when we create a p-n junction. And what is the meaning of this, this intermediate region? So this is the intersection, yes, but what is this, the meaning of this part? It is, let me call it, depletion region or depletion zone. This is called depletion region. Depletion means the free holes and free electrons are swept away. They are pushed away from this region. Why? Because of the diffusion. Remember that we had, let me go back to the previous picture, we had immediately, just before this junction occurs, we had several, since this is, remember this left hand part is free P and the other part is N. In the N part, there are free electrons. So there are several much more free electrons than there are. I'm not drawing these ions in the previous picture. To make it simpler, I'm only focused on the free carriers. Ions are not carriers. The carriers are free electrons and free holes. So for the N-type we have so many red dots, free electrons with respect to the black ones, and in the P-type we have so many free holes, but a few red ones, free electrons. But when you join them, because of the difference in the concentrations, just like we had dealt with in the previous case, previous lecture for the diffusion, so these free electrons and free holes try to recombine each other. When free electrons and free holes meet, they recombine. What is the meaning of this recombination? For example, a free electron is a person standing in a hole, in a room. And a free hole is an empty chair, empty place, seat. Okay? So if in a hole there are some people standing and who want to sit down, but there are also some empty places, empty seats where someone can sit, then those people try to go and sit down. But if there's no place to sit, then they wait standing. So if these free electrons are the standing people and those holes are the seats, empty seats to be sat, then when they join, when they recombine, the number of standing people and the number of empty seats get less and less because they combine, they recombine. It's called recombination. Let me join them. Consider this as that single p-n junction. So these particles move to the other side because there's a very large concentration of free holes, and these free holes and those electrons are just recombining, so that in this part, up to some certain limit, because this limit is this is on the order of some, let's say, micrometer maybe, very short length. However, there is no free electron, no free hole in that part. So this is the whole depletion zone, depletion layer, depletion region. It has a thickness of around 1, let's say, micrometer, 1,000th of a millimeter, very, very thin region. All right, but on the other hand, there are ions. Ions are not influenced by this diffusion. Ions are there because these positive ions are the ones, the atoms that have lost their electrons, and the other red circles are the ones that have gained an additional electron, so that they are not affected by this recombination process. So in this part, as you see, there is no single dot. Red dots or black dots do not appear. But in the outer regions, there are both types of carriers, there are both types of carriers, one type of ion there, one type of ion there. So this is the main picture for the p-n junction. But what happens then? And why don't these free electrons go further to the end? It is not possible because of the electric field now occurring as a result of these charges. Because here we have, as you see, a layer of positive ions and a layer of negative ions. From the positive to the negative, there occurs a certain electric field. And remember that electric fields try to move the holes in the same sense, but move the electrons in the opposite sense. So these electrons, which are already moving from the right to the left, from N to P, since there is an electric field there, occurs a force on them to stop them before going further. So until an equilibrium is established, there is a diffusion, but that diffusion has a certain pair of limits. So this part is called depletion region, where there are no free carriers of either type. However, there are ions, and those ions create an electric field to stop the carriers to go further and further. So this is also the contact potential resulting because of the depletion of the free carriers from that intermediate region. Now let us compare these three cases as far as the free carriers are concerned. Case 1. So let's consider this picture again. Here we have, let's say, from the P, always we have the P type on the left and N type on the right in these pictures. So these are the carriers, which are the minority carriers, and this is called I drift. And this is the diffusion. Some carriers having enough energy have a tendency to move from the N type to the P types part. What about the middle case? Forward bias. Now we have a flatter hill, less steep than the first, by this amount EV. So this is the hill. Now, case 2. So we have a hill, but it is less steep than the first case. And there are so many carriers having enough energy now moving to the left-hand part. I drift, this is I diffusion. So if you compare the two currents, let me show by some arrows. So this is the case I drift, and that is the one I diffusion. They are almost the same. Diffusion and drift currents are almost the same in case of no bias. But in case of forward bias, where we join the positive end of the battery with the positive part, negative end with the negative part, then this hill is less steep. In such a case, we have again the same number and same current for the I drift. Because drift current is not affected by these potential hills, so this is called I drift again. But this time we have a much larger I diffusion because of this shorter hill. However, in the last case, case 3, reverse bias, we have a much steep, I can just show one part of it only. So these are the same carriers. So I drift is the same. I is the same. However, here we don't have enough number of carriers having sufficient energy to surpass, to overcome the barrier, so that maybe there is no diffusion current, or maybe very little, maybe this much. This is just I diffusion. Okay? However, in each case, drift current is the same. It is not affected by these potentials. It is because of the minority carriers and because of the built-in potential electric field within the diffusion region, so that those carriers are moving. They are influenced by the temperature maybe. Otherwise, because of these potential sources applied forwardly or reversely, they are not affected by such external potentials. However, diffusion current is strongly influenced by those potentials. If there is no potential applied, they are just equal and opposite. But in this case, I diffusion is much greater than the drift current. However, here it is just the opposite case. Drift current is still the same, but diffusion current is either nothing or very little with respect to the previous diffusion currents. And what about the mathematical implications? Let's now consider the exponential function corresponding to these, and then we can finish this part. Now compare these three cases mathematically. What is the function in each case? We have, anyway, N and conductivity and sigma current are corresponding terms. They are proportional. So the number of free carriers here is proportional to the current occurring. Therefore, in case 1, we have some number. Let's say this part is e to the, what is that? EF minus EG minus E phi. Phi is this part. E phi is this additional part because of the contact potential. So in this case we have, in case 1, we have something proportional to EF minus EG minus E phi over KBT. But in case 2, we have an additional external battery. So this part, remember, corresponds to E phi plus EV. So this plus means it's a negative term here. In this case, we have something proportional to e to the EF minus EG minus E phi but minus EV. Minus E5 plus EV over kV. In other words, it is the same function here. Let's call this, for instance, I0. So here we have something proportional to previous I0 and this additional part. This additional part does not appear here. I0 e to the EV over kVt. But in the third case, reverse bias case, we have e to the EF minus EG minus E5 minus EV over kVt. In other words, it is proportional to previous I0, this full part, times this is either e to the EV over kVt or e to the minus EV over kVt. Remember that this e in the exponent corresponds to the charge of the electron. However, this is the exponential function. So this is the important part. It is either a positive exponent or a negative exponent in the two cases. If it's a positive exponent, we have much greater diffusion current in one sense. If it's a negative exponent because of the oppositely applied potential from external source, then we have a negative exponent and the current drops almost totally. So we understand that this is called a diode. This is also called PN junction. Now this is called, in this case, it's a diode. It's a one-way device. So a diode in the it has a certain symbol like this in the circuits. So it passes the current in one way but blocks it in the other way. A diode conducts electricity in one way and blocks in the opposite way, in the opposite sense. So this part, let's say in the schematic way, we can consider that one end should be at a sufficiently higher potential to conduct electricity than the other end. So it can be used as a gate for us, as a switch, on-off type of thing. So, for instance, this is the, let's say, point A, point B. VA should be greater than VB by some amount, minimum amount, so that if this occurs, if VA is greater than VB, then it is on. So the current is passing. If VA is less than VB, it is off, which means there is no current. For example, it can be applied used as a rectifier. For example, a sine wave, for instance, a sine wave like this. If it is applied as an input to such a rectifier, for instance, in the first part where this is a positive potential or positive current, then it conducts. So the result will be, let's say, maybe this part is on, yes, but then zero, then on and then zero, etc. Because in these second parts of the cycle, the other part, for instance, if you apply in a very simple picture, if you have such a sinusoidal source, then in this part where potential is positive, so that this part is more positive than the other part, so it conducts electricity, it lets the current pass, so that the output is like a replica of the input. It's a sinusoid. It is also a sinusoid. But in the other part, second half of the cycle, this part is more positive, so that second condition is met. Therefore, it is off. It is off means there is no passing current, and it continues in this manner. So this is a very practical and a very simple device, and it is also used as a later on we can learn the transistors and different kinds of transistors for different purposes, other electronic devices. But this is just the sort of alphabet of those more complicated electronic devices. So PN junction is quite important in that sense, and possibly we finished the term here for this term. Physics 412 has ended. Thank you.